Okay, good. And the two, but the sound, then there won't be any sound.
It's from me.
So,
The Discord here didn't mute. I think you can record the sound from here, but just a little bit far. I think you can get the sound.
yeah. Discord, because it shows green, so this mic has sound. This one doesn't.
Oh,
Um, so actually, it's okay, I think, because yes, because the recording would be from OBS Studio. So OBS Studio should should do the recording, not Discord before it gets to Discord. So that should be okay. Okay, good. So today, what I want to do in class is, last time we talked about forward kinematics, so now we want to be able to implement that on our real humanoid robot in 3D. So we have a little robot here, a small one, which is from the company Robotis, and you should try and develop the forward kinematics first for the right arm. Those are a little bit more interesting, and then after you're done with the arm, then implement the kinematics for the legs so that we can, and then the head is pretty, only has one degree of freedom, so cannot really do any kinematics there. But you want to be able to work out where the joints are, which means you need to measure the distances between the joints. So either look up on the internet the width of these servos, or I have a measuring tape here. You can measure it yourself to confirm, and then implement the forward kinematics, just like we discussed, with our with the same approach that we used last time, except now for this one we did it only in 2D. Now we want to implement it in 3D. So we were working on this project for the first part of the class. Which means that you actually have to do some work. So you need to get up, have a look at the robot, check the distances, and then start thinking about how you would structure the program in order to be able to do that. Let me just see where my measuring tape is. It's robot vision. Yeah. We'll just switch to the discussion. Yeah, you can just drag and drop people into the right chat. I think. So at the end of the class today, you want to be able to draw this in 3D, this kind of figure in 3D for this particular humanoid robot. Yeah. Okay. I mean, it actually did look at. Yeah. So first you need to figure out which way the joints are actually moving, the distances between them afterwards.
But this is not the one. It's just
Go to the lab and get a measuring tape? Because I don't have one. I usually have one.
you mean
The ruler. Yeah. Or ruler, if you have a ruler. Did anybody bring a ruler by any chance?
no more ruler, or it's just
Yeah, this one will do.
it's a little bit.
Yeah.
Yeah. Or I take another one.
Yeah, take another one.
Okay.
Because if we do it, we might as well do it right. I usually have the IKEA measuring tape on me in my wallet all the time. I don't know where I lost it. So.
I also can't find my coffee mug anymore, so weird day today.
Oh, this one, yeah. Okay. So we have a measuring tape, so you can measure your robot.
Yeah, but my top question is this definition, two kinds of definition. Because my rendering is the same. Because these two are from and my impulse one to minus one. I previous my notebook is like this. From my notebook is like that.
It's always from it's from the starting position to the answer. So like this one is from the base, or this one is from the previous one, or this one is from this is here. So always the from so we have a C cable here. USB-C, yeah. Data or just power?
Power, I think both is okay. You can also
Okay. Because the internet is a bit slow.
it's really slow.
Yeah, let me see if I can copy it. So, for example, let's take this is the
Yeah, yeah.
so first you have all I see that it's pretty different.
So,
And then you want to okay. So now the picture is
I think it's one of the problem I made.
so look first you can don't focus on the logic. If you cannot control this in your head, you cannot do anything with this. You cannot control. So first you have to put a Z axis on every joint. Okay.
Yeah, so it's about if I have a joint, I should find the here or is it. If it's okay, I should put
Yeah.
it always to this.
Yeah. So good. So it's the all the Z. The easy word. The Z is the easy. Z. Z.
Just one of these is okay. The people.
Yeah, always in the rotation in the center. If you
This is also.
I should be just what you make an adjustment at the point of view. Maybe the angle should be reversed after. But we'll just reverse the angle. Then the other one that is always the one. So the only thing is you can here yeah, the right angle is the right issue. So I think I don't know what you is and then you see the new this actually, we will just like get all the macros. We will just keep
One of the numbers.
here is really easy to work, so you can by yourself. It's better to learn it because then because here you already know this, you can use math to this directly but if you learn this, you use the column or the
I think
yeah, that's right. So this is the axis the x-axis is an equation to x-axis and y is the and we use these yeah, the x we can only set this impulse is very hard to see sometimes because the channel normal. So you have to simulate z rather than earlier playing.
Right, so have a look at it. This is the robot, here's the picture. So first of all, what you want to know is how many kinematic chains do we have for this robot? Yeah, I guess I have to. So that it becomes more apparent. So kinematic chains means that the movement of some joint will affect the joints further down in the chain, but not the other joints. So that means that we will have 5 kinematic chains. We have the left arm, the right arm, the 2 legs, and the head. So in total we have 5 kinematic chains on this robot. Because if that shoulder joint moves in the left shoulder, then these joints are going to be moving as well. But all the other ones are not going to be affected. Similarly, if our right leg moves, then all of these joints are going to move in space. But these remaining joints here will be unaffected. So we have 5 kinematic chains. Then the next thing you want to do when trying to develop the kinematics of the robot is the next step usually is to try and decide where I want the inertial frame to be. Where do I want 0, 0, the origin of the humanoid robot, where I want to attach that. And any suggestions? What would be a good place to specify that this should be the origin of the humanoid robot? So clearly, putting the origin of the robot anywhere on the end effectors doesn't make sense, right? Because otherwise, if I move my hand, now the position of the robot will have moved in the work coordinate system. Whereas what I really want to reason about is the position of the robot with respect to the workspace. Right? How close is it to the wall? How close is it to the table? Can it pick the ball or something like that? So I want to have a point that is not part of any of the kinematic chains. Now, when the robot walks, one thing that would be pretty nice as far as the work coordinate system is concerned would be to place it here in the middle between the 2 feet, because when I reason about the robot walking, then that would be the ground that the robot is walking on. But the problem is that that point, then when I reason about the robot, because the legs, we can bend the knees, this. So then that means all of a sudden the other coordinates of the robot all depend on the height of the legs. So usually we don't use that point as the origin of our robot, but we pick this point here, the bottom of the torso of the robot. When the robot can move through the world, I can calculate distances to walls and things like that without any changes. I don't need to take the position of the arms or legs into consideration if I just want to measure how far it walks or something like that. So that's the most common origin for the robot. Then we need to decide about the axis. How do we want to align the axis for the origin of the robot? So any suggestions? So now I know where I want the origin to be. I just need to figure out where X, Y, and Z, where those axes are pointing to. Now, for the coordinate systems attached to the joint, we have a very strong convention that the axis of actuation corresponds to the z-axis. That's what we discussed last class. Which means that if I have a coordinate system, x, y, z, x, y, Z, make it a right-handed coordinate system. If I have one like this, then for this particular joint, Z will have to point in this direction or in that direction. But it would be parallel to the axis of rotation here. That's what we rotate around. So our Z coordinate in the joints is fixed. But the coordinate system of the humanoid robot, that doesn't, there's no actuation, so I don't really need to align it in that way. So then most people would agree that z-axis being up is sort of a very human-like, very intuitive alignment of the coordinate system. So for our torso, we want the coordinate system z to go upwards. Z is height of something, right? So if the robot is getting taller, then the z-axis value should increase. So we keep z this way. So now I still can rotate around the z-axis. And then it doesn't become, it becomes less clear maybe, but this one is not the right hand. X, Y, Z should have this. So the question then is the robot moves forward? Also, if the robot walks, I think it makes sense to have the coordinate system aligned so that one of the axes is pointing in the direction that the robot would walk when he walks forward. It doesn't make sense to have the coordinate system aligned this way or this way. So Z goes up, then X seems a reasonable choice for if the robot moves forward, then he moves along the Z-axis, the X-axis, which then means that the Y-axis is pointing to the left. So that would be the origin of the coordinate system that we have with most humanoid robots. And attached to the bottom of the torso, exactly down here, the part that doesn't belong to any of the human things. So that's our 0, 0 point of the robot. Now, that when you work with the kinematics, I'll let you experiment with it more, and then you'll see what one of the problems with kinematics for humanoid robots is. So first of all, attach the coordinate system to the torso of the robot, x being pointing forward, y to the left, and z going upwards. And most people do it this way. Z being upwards being a very strong convention. X and Y, sometimes you can flip them if you want. So X is pointing forward, Z pointing upwards, and Y is pointing to the Y, Z.
So this one is not good because it's the same. So now we need to use this and this. Uh, so all this is this. So there's more. Only this. But maybe you can take the others. No, only this is. That's okay. So now we have to go here and all of this. And so we need to one with the less and less. You know what I mean? But if I do this, I'm like, this is. It's the they don't have the same convention, so it's hard to talk. X and X and they don't have the same. It's always blue. It's always blue. X is always red and Y is always blue. That's it. Oh, okay. So, no, we are and then to move to this one, we turn along the Y. Okay, and then we choose to go here or go here. But we can undo whatever we want. Yeah, we can do that. This stuff. Okay, now the next one is on so we can choose between 7 and 5. So, just like this. Oh, that's it. Yeah, yeah. So I change it to the just one. We can also do this. This one is not fixed. Yeah. This way. And then the white, the old white. So the white changes. So one is down. So one and
Right, so then the next step, you want to look at the kinematics of your robot. Have a look at how many degrees of freedom you actually have. So for the right arm, we have 1 degree of freedom here, 1 degree of freedom here, 1 degree of freedom here. And then this is all fixed, there's nothing. So we have a total of 3 degrees of freedom in each arm. Now this robot is a little bit special compared to other ones because, or what you would expect, well, first of all, the rotation here, the axis of actuation for the first joint, which would be, well, this is ID2, this is ID13. So this will be, for this particular kinematic chain, this will be joint 1, joint 2, joint 1, joint 2, joint 3. This one is joint 1, joint 2, joint 3. And link 0, what are the links then for this kinematic chain?
The body. The body.
The body?
Yeah, the robot. I mean,
The links, yeah, they describe the body of the robot. But for the kinematic chain of the right arm here, I have 3 joints. So we would label them joint 1, joint 2, joint 3. I have 4 links. If I have 3 joints, and I usually have 4 links. So what is link 0? What is link 1, link 2, and link 3? Link 0 is the link last class. Link 0 is the link from the inertial frame to the first actuator. Link 1 is the link from between joint 1 and joint 2. Link 2 is the link between joint 2 and joint 3. And link 3 is the end effector. So that would be this part here. And then there's no more joint there. So link 0 would be the geometry from here, from our origin, to this shoulder circle. And also, we can start assigning our coordinate systems for the joints. So here, the z-axis on joint 1 is going to point this way, or 180 degrees rotated. Right? Those are the two possibilities that I have here. Yeah. Then joint 2 would be like this, and joint 3 would be like that, like an arrow pointing out. Because these two are offset by that. So now I know where my z-axis are, or where I want them to move. Now, if you've done the robotics course, a different robotics course before, you may have heard of the Denevit-Hartberg convention. That's a convention that is very popular with industrial robots because their kinematics are sort of quite standardized, and it works very well for them, which allows us to express all the transformation matrices using just 4 numbers. There's a special way that we need to assign coordinate systems instead of having a 4 by 4 transformation matrix of homogeneous coordinates, which means that we have 16 unknowns. Right? To go from here to there, I know guaranteed I can do it with a 4 by 4 matrix. So 4 by 4 matrix has 16 numbers, so the only tricky part is how to find those 16 numbers. There's a convention called Denevit-Hartberg that makes that a little bit standardizes it, so you can do this transformation with 4 numbers. But for humanoid robots, that convention doesn't really work quite so nicely. So for humanoid robots, I usually just use the elementary transformation matrices and then compound them in order to develop the kinematics. So if if I have this particular robot here, and actually, yeah, I forgot about the torso joint. So this is actually the joint that is shared between these 3 kinematic chains. So that's actually the first one we should model. True. And then I drew it. So the first joint that we actually have is first joint is here. I need to have one z-axis there, but it's aligned with the z-axis. Now, our torso joint then, that will be joint 1. Our first link will be from the 0, 0 location from our origin to this servo motor tree. So,
you can put this in the Yeah. So this one is the reverse. Because no we can. So no we can.
If they have the
Actually, all okay. W250.
so so here's the CAT information for the servo motors. They don't have one for the entire robot, which is why we need to develop the kinematics in the first place. But that's what we would be interested in. So if I put 0, 0 at the front of my robot here, exactly where that LED is, then the axis of orientation will be going upwards, axis going forward, but the axis where the torso rotates will be set back a little bit, because that's where that hole here is. If we look at the cap information for that particular servo, then it would be from the top to this center here, which is 11.25 millimeters. So to get from our inertial frame to our frame, to our first joint, would be a translation only. I don't need to do any rotation. The z-axis is already in the correct direction. And it would be, x would be negative 1.25 millimeters, and z would be the height of the servo, which is
or you can just look at the dimension of the electron that is because you can do this. So usually I can whatever the be sure to that you know
34 millimeters for the height of the servo in the Z, yeah. Because in here it doesn't actually show. Like it should be this part here, which is missing. Oh no, sorry, it's here. It's 34. Yes, I just saw it wrong. So it is there. Yeah, 34. So if you want to translate that into code,
so for instance here the English chunk of objective because you see objective only leads to transformation and the rotation is the term so basically it's very easy to just going up. So it's literally way faster for this one. Because you just put it as a meter and then put it
what did we have for distances? So I'm just going to define some constants. The servo width is servo height was 34 millimeters. So I do the drawing all in millimeters. See how that. So then servo width is 28.5. And the length is 46.5. So 6.5 is the length.
Parece que meu próprio text
Yeah, that's why. I see the pictures and it's just